Hi everyone, we're going to do another calorimetry problem, and here goes. An aluminum calorimeter cup contains 225 grams of water. The cup and the water are both at room temperature at 27 degrees Celsius. A 400-gram sample of silver at an original temperature of 87 degrees Celsius is placed in the water. After a couple of minutes, the system has reached thermal equilibrium, and the final temperature of the mixture is 32 degrees Celsius. Calculate the mass of the aluminum cup. So I'm going to draw a little bit of a sketch here just so you get an idea of what's happening. If you have a lab portion of this class, this calorimetry problems you're going to do are going to look very much like this. So before, what we have is we have an aluminum cup, and it has some sort of water in it. And the two of them have been in contact long enough to reach an equilibrium temperature, and the original temperature of the aluminum and the water is 27 degrees Celsius. We do not know the mass of the cup, so the mass of the aluminum cup, that's our big question mark. The mass of the water we know is 225 grams. We also happen to have a hot piece of silver. It's been heated somehow, and Ag is the atomic symbol for silver, so that's what I'm going to use. The mass of the silver is 400 grams, and the original temperature of that silver happens to be 87 degrees Celsius. Afterwards, here's what's going to occur. The piece of silver is going to be placed into the water, and that's going to be placed into the aluminum cup. So all three of these things, after a few minutes, heat is going to transfer. It's going to obey that second law of thermodynamics. Heat's going to go from the hot thing to the cool things. We're going to assume no heat is lost to the environment, and the entire mixture is going to reach an equilibrium temperature of 32 degrees Celsius. And my question is, what is the mass of the aluminum cup? So let's set this up. We're going to use one more time. The big idea is law of conservation of energy, and we're using this applied to heat, which is which is the first law of thermodynamics, which is conservation of energy as applied to heat. And so this is going to be the heat that is lost is going to be equal to the heat that is gained. So let's analyze the situation and see who actually has lost heat. Well, we started out with a hot piece of silver, so it's going to be the heat lost by the silver. What has gained the heat? Well, both the water and the aluminum cup have both gained heat. So heat gained by the aluminum, Al is the atomic symbol for aluminum, and of course H2O is water. Every time we have heat changing temperature, we're going to use our equation for quantity of heat, mc delta T. So I'm going to write an mc delta T, one for the silver, one for the aluminum, and one for the water. So let's change pen colors. Here goes. Heat lost by the silver. This is going to be the mass of silver, specific heat, silver, change in temperature, silver, is going to be equal to the heat gained by the water. So this is going to be the mass of the water, specific heat, water, change in temp, water, plus mass of the aluminum cup, specific heat of the aluminum cup, and change in temp of the aluminum cup. Now, as mentioned in the last problem, if you're going to set them up in this format where heat lost equals heat gained, the only thing you mathematically have to do to make sure this works out is you have to make your change in temps positive values. So let's think about it. Your silver, is it going to have an original temperature or a final temperature that is going to be bigger? Well, we happen to know it starts out at 87, it ends at 32, so the change in temperature of the silver is 87 minus 32. For the water, the original temperature was 27, final was 32, so the change in temp of the water is 32 minus 27, and the same over here, 32 minus 27. The aluminum and the water are in thermal equilibrium, and that means enough time has passed for the aluminum and the water to have that same temp. All right, now let's put the rest of our numbers in. So mass of the aluminum, we were told the mass of our aluminum is 400 grams, so that's going to be 0.4 kilograms. I'm sorry, I'm saying aluminum, but I'm pointing at silver. My bad. So mass of silver, 400 grams, 0.4 kilograms. Specific heat of silver, you can look that up on your physics constant sheet or in your textbook or online, and that should be 233 joules per kilogram degree Celsius. And our change in temp is 87 minus 32, and 87 minus 32, you know what? I'm going to cheat and use my calculator because I don't want to say the wrong thing. And that is 55 degrees. Now I am going to go forth, before I try and do all of the right-hand side, I'm going to get a mathematical number for this so I don't run out of room on my page. Kilograms will cancel, degrees Celsius will cancel, and if I multiply those three things together, I am going to end up with a number of 5,126 joules. This is all of the heat lost by the silver. That's this whole side. Now this is going to be equal to the heat that is gained by the aluminum and the water. So I'm going to pull this down, mass of the water. Mass of the water, we are told we have 225 grams, so 0.225 kilograms. Specific heat of water, 4,186 joules, kilogram degree Celsius. Where did that number come from? From your constant sheet or looking up the specific heat of water. Change in temp water, well, 32 minus 27 is 5, plus the mass of the aluminum cup. Oh, that's what we're solving for. So mass of aluminum cup. Specific heat of aluminum, I looked that up on my constant sheet or online or in the book, and that is 900 joules per kilogram degree Celsius. And the change in temp, 32 minus 27, is 5 degrees Celsius. Okie dokie. Let's simplify 0.225 times 4186 times 5. All of this together should be 4709 joules. Kilograms are going to cancel. Joules per degree Celsius. This comes down, so 5,126 joules, plus mass of the aluminum cup, 900 times 5, well, that's going to be 4,500. Degrees Celsius will cancel. Joules per kilogram. I made a boo-boo on my units, didn't I? I can hear some of you yelling at me. 5 degrees Celsius, I didn't cancel those, so that should go away. We're getting very close to the end. Let's clean this up. Now, I want to solve for mass of aluminum, so what I'm going to do is subtract 4709 joules from both sides. When I do that, the left-hand side ends up being 417 joules is going to equal mass of the aluminum cup times 4,500 joules per kilogram. So mass of the aluminum cup is going to be equal to 417 joules divided by 4,500 joules per kilogram. Joules will cancel. Kilograms are in the subbasement, which means they're going to come up. And when I do this, I got 0.0927 kilograms, and that is 92.7 grams, which is a logical number for a mass of an aluminum cup. All right, take care. See you later.